Hi, so now we're going to practice finding our first one sample Z interval. So we take a look at this problem. What you have is the measurements of a bunch of crankshaft diameters. Crankshaft's a particular part of an engine. It says the data come from a production process known to have a standard deviation of sigma equals 0.060 millimeters. So you can see that. Let's just get my pen up here. You can see that right here. That's a population standard deviation. So we learned when we did z-tests and t-tests that if you have the population standard deviation, then it's going to be a z interval. If you had a sample standard deviation, you would do something called a t-interval, which we haven't learned yet. So when you build a confidence interval, one thing you're supposed to do is check your assumptions, the same assumptions you would check when doing a significance test. So number one, we're supposed to have an SRS, which presumably we have here. Number two is to check for independence. And when checking for independence, you want to know that the population of all crankshafts is greater than or equal to 10 times the sample size, which in this case, there are 16 measurements. So that's 160. So we have to assume that more than 160 of them are made. If that's true, then we know the standard deviation of x bar is equal to the standard deviation of x divided by the square root of the sample size. So if we look back at the problem, you can see that standard deviation is 0.060, and we know the sample size is n equals 16. So we can plug those things in here, 0.06 over the square root of 16, which, if we calculate, we get 0.015. All right, and the third assumption is normality. Now, unfortunately, the sample size here is not large enough. N is only 16, which is not greater than or equal to 30. That's what I'm trying to write there. So we have no central limit theorem help. So we're supposed to check a box plot. Now, I don't have the ability to show you my box plot, but if you take the time to type the stat into your TI-84 calculator and you do a box plot with that, the graph you get looks pretty good, actually. I'll attempt to draw a little picture of it. You only see very slight skewness to the right, minimal skewness. Probably one of the best box plots we've seen so far. So that means it's safe to use the Z interval. Okay, in part B, they want us to give a 95% confidence interval. So we know in general, our confidence intervals look like this. It's X bar plus or minus Z star standard deviation of X divided by the square root of N. So I've already done some of the one variable statistics here, which you would need to do. And if you do that, you'll get an X bar of 224.002 plus or minus. I'm going to leave Z star out for now. And then we already know that this thing, after doing our assumptions and our independence check, turned out to be 0.015. All right, so the last thing left to do is figure out what Z star is, and that's always going to depend on your confidence level. It's super important. Z star always comes from the confidence level. So keep that in mind. I'm going to draw a little normal distribution here. And if we put 0.95 in the middle, because this is a 95% confidence interval, then we need to know what Z score goes here and here. Well, just remember the symmetry of the normal distribution. It has that perfect line of symmetry down the middle. So what that means is that in this tail here, for example, we could do 1 minus 0.95 and then divide by 2. And what we'd find out is that this tail has an area of 0.025. And so does this one, actually, 0.025. And what we want is we want the z-score that would capture those areas. You do that by using either the chart in reverse, look in the normal chart, and look for an area of 0.025, or use inverse norm in your calculator. And if you do inverse norm the calculator, you're going to get z equals negative 1.96. You just put the positive version of that in here, 1.96, and there you have it. That is your confidence interval. Now you should actually compute this, which we're going to do now. And if you type this all in, and let's see what you get. You get as an answer this 223.97 to 224.03. So what we can say is that we're 95% confident that the true mean has been captured in this interval. And that's sort of a promising thing because we look at the problem. The problem said that the mean was supposed to be 224. And you'll notice that 224 is definitely in this interval. So that means that we would not reject that the mean is 224. We would say it could be 224. A confidence interval does not contradict that. And that's a good thing. Okay, more practice problems to come.